I want to look at a few more examples that involve rewriting the function. In the same way rewriting a function before taking a derivative can make it easier to take that derivative, so too can rewriting the function before integration make the integration easier. So let's take a look at the integral of 1 over x cubed dx. So this is going to be the same as the integral of x to the negative third power dx. And now we just apply that exponent rule that we learned earlier. So all we do is we add 1 to the exponent. So negative 3 plus 1 is negative 2. And then we divide through by negative 3. So we have 1 over negative 3 times x to the negative 2 power plus c. And the next one we want to look at is the integral of the square root of x. So we can rewrite this into exponential notation as the integral of x to the 1/2 power dx. And we apply the same rules that we did earlier. We begin by adding 1 to the exponent. So we get x to the 3/2 power. And then we divide through by the exponent. Now dividing by a fraction means you have to flip the fraction. So if we want to divide by 3/2, we end up multiplying by 2/3. So we get 2/3 x to the 3/2 power. And then we add our constant of integration. Next examples I want to look at involve distributing the integral over addition. So the integral of x plus 2 dx, well, because the integral distributes really nicely over addition, this is the same as the integral of x dx plus the integral of 2 dx. The integral of x dx, we've done this before. We just add 1 to the exponent, and we get 2, and then we divide through by that new higher exponent. So we get 1/2 x squared plus, and then the integral of 2 is just 2x, and then we add a constant of integration. Now, one thing to note here is that you may be tempted to write, let me use a different color here, you may be tempted to write 1/2 x squared plus c plus 2x plus c, and you add a constant of integration to both things. But here, if you have c written on both of those, that implies that both of these have the same constant of integration applied. So if you're going to do this, we need to change one of these to be, say, a k or some other constant. But if we have two constants here, c and k, we can just add them together to get one overall constant for the function. So if we had something like this, we could rewrite this as 1/2 x squared plus 2x plus, call it h or something, where h equals c plus k. But remember, names of variables don't really matter, so this h and this c here are the same thing. You only need to add one constant of integration. Let's take a look at one final example here for this video. Let me go back to black. We want to find the integral of 3x to the 4th minus 5x squared plus x dx. So remember, integrals work really nicely over addition and subtraction. So this is the integral of 3x to the 4th power dx minus the integral of 5x squared dx plus the integral of x dx. And now we just do that same power rule that we've been doing this whole time. So for here, we just add 1 to the exponent, so we get x to the 5th, and then divide the coefficient by that new higher exponent. So we have 3/5 x to the 5th, minus, bringing down this minus here, the integral of 5x squared. So we add 1 to the exponent, we get x cubed, divide the coefficient by that higher exponent. So we get 3/5 x to the 5th minus 5/3 x cubed, plus, and then the integral of x, as we've seen before, is 1/2 x squared. And then we throw on our constant of integration. So we have 3/5 x to the 5th power minus 5/3 x cubed plus 1/2 x squared plus c.